Okay, so let's talk about decay models now of if the K is less than 0 or negative, then the size of the sample is decreasing over time. So the formula looks the same. A of t equals a sub 0 e to the kt, but now k is a negative number, where again a sub 0 represents the initial amount, or the amount you started with, how much you began with. K represents now an exponential decay factor. And T represents time. And again, make sure you remember that your K and your T need to match units, days, years, whatever it is. So one of the most common uses of this formula is analyzing radioactive decay. If you have a pile of radioactive material, as the unstable atoms try and get to a stable form and throw off electrons, that actually decreases the mass of the pile of material. So energy is released. You may have seen E equals mc squared. So energy is released, so that means the mass is going away from the pile and it's decreasing in size. So radioactive substances have something called a half-life, and it's a number that says how long it takes till the amount of the substance is reduced by half. So if you started with 100 grams, after the half-life goes by, then you have only 50 grams left. So that could be 1,000 years, it can be 2 hours. It just depends on how radioactive the substance is. Okay, so here's an example where the half-life of radioactive potassium is 1.3 billion years. So here's a good use for scientific notation. So billion, let's see, if I have 1,000, then a million, then a billion, this looks like 1.3 times 10 to the 9 to get billions. So this is the half-life. So this is how long does it take until half of what you started with is what you have now. So if 10 grams is present now, so A of t equals A sub 0 e to the kt. So if 10 grams is present now, that means I started with 20, right? Does that make sense? If I started with 20 and now I'm at 10, I have e to the k 1.3 times 10 to the 9. And I'm trying to solve for the k, the exponential decay factor. So I'm going to divide both sides by 20. This number is always going to be 1/2 when we're talking about half-life, because we're always talking about when we have half left. So then you're going to take the ln of both sides. So the ln of a half equals the ln of e to the k times 1.3 billion. And we know this equals k times 1.3 billion from the problems we've already done. So then I have that k equals the ln of 1/2 over 1.3 billion, which is a tiny, tiny number. Let's see, how big is that? Wow, it's negative 5.33 times 10 to the minus 10 in scientific notation. So that's our k number. So now we know that our formula looks like A of t equals how much you started with, A sub 0, e to the negative 5.33 times 10 to the negative 10 t. So then the question says how much will be present in 100 years. So if 10 is now, and we want to know in 100, we're saying A of t equals 10 e to the minus 5.33 times 10 to the negative 10 times 100. So let's see how much it has decreased in 100 years. I'm going to suggest you figure out how to save this number in your calculator so that you can use the actual number and not a rounded off number, because it can make a difference. So I'm getting approximately 10.00 grams. So it hasn't really decayed enough to notice yet. But then if we do, what about after 1,000 years? I'll let you do that one. This should say A of 100, sorry. I'll let you do A of 1,000 and I'll tell you what I get and see if you get the same thing. So I still get about 10.000. It takes until a lot of decimal places before I get something different than 10.0. So this is a really long half-life. So maybe if we did 1,000,000, let's do 1 times 10 to the 6. So that's 1,000,000. So then I'm going to get 9.995 grams. So after 1,000,000 years, you've barely lost any. So this is not a very radioactive element. So radioactive potassium is not very radioactive. Okay, so now let's look at logistic models. And this takes into account that usually there isn't unlimited food space or whatever, and that there are some kind of limitations on the amount you can grow to. And so this is called a logistic model. It says the population P after time t is given by this function c over 1 plus ae to the minus bt. So the a and the b and the c are constants that represent some particular scenario. The a is positive and the c is positive. It's a growth model if b is positive. Oh, that's interesting, but it's in the denominator, so I guess that kind of makes sense. And it's a decay model if b is a negative number. C is called the carrying capacity, and it's some kind of upper limit on the population because of some kind of restrictions, food or space or something like that. B is the growth rate if B is positive, and the decay rate if B is negative. Okay, so this is what the graphs look like. So this is a logistic growth. And you have this interesting point called an inflection point that happens. And this is logistic decay. Okay, so here's just an example of using the model of, it asks you to put numbers in here. So first it says, what is the growth rate? So we look back and say, let's see, what was the growth rate? The growth rate was the B. And the negative is in the formula, so the B equals 0.799. And so this is actually 79.9% per year. So that's the growth rate in percent per year. And then what was the percentage in 1990? Well, let's see. They're saying let's use a scale where the year 1984 is t equals 0. So the year 1990 is going to be the year t equals 6. So I want p of 6. And I want you to go ahead and plug that in and see what you get and see if you all agree. And then the D part's the hardest part here, I think. It says, during what year did the percentage reach 90? So you're asking, when does this get to 90? And you can see this is going to take some solving work because I want to solve for the T, but it's in the bottom. So I talked about that earlier of if what you want is in the denominator, you should multiply both sides of your equation by that denominator. So we're going to multiply both sides. So I'm going to have 90 plus 90 times 3.014 e to the minus 0.799 t equals 99.744. Well, remembering that we want to isolate the exponential, we need to subtract 90 from both sides. Get 90 times 3.014 e to the minus 0.799 t equals 9.744. Then we're going to divide by 90, divide by 3.014. Okay, so now I have e to the negative 0.799 t. And I'm not going to round this off yet. Don't ever round off until the very end of a computation. You can really mess up your answer. So now I'm going to take the ln of both sides. And we know that the left side is going to be 0.799 t. The ln of all this stuff. And then I'm going to divide by negative 0.799. And let's see if we get something that makes sense for t. And I'm getting about 3.3. And I'll look back at the problem statement, and it looks like that's years from 1984. So during 1988, right? From 84, 85, 86, 87. So during 1988 is when we would expect that the percent of users reached 90%. So that's it for this section.